Okay, so now we're going to have a go at a past paper from 2018, and this is AQA Chemistry Paper 1. But what I would suggest and highly recommend is that you download this past paper first of all from the link below and have a go yourself. In this first question, we have an electrolysis cell, and it says a student investigates the mass of copper produced during electrolysis of copper chloride solution. And we've got our diagram, and the first question is which gas is produced at the positive electrode? So if we've got copper chloride solution, the negative ion would be the chloride, so that would produce chlorine gas. In this next question, we've got to calculate the mass X of copper produced in experiment 2 after 5 minutes. And we're going to have to use our table on page 3 to help us do that. So when we look at our table and we look at 5 minutes, we have the masses of 3.02 plus our mass of X plus 3.01. So all of those three added together, then divided by 3, will give us our mean mass of 3.06. So if we rearrange that, then we would get that X would equal 3.06 times by 3, take away 3.02 plus 3.01, and if we calculate that out, we get ourselves an answer of 3.15 to be the mass of X. In this next part of the question, the copper chloride solution used in the investigation contained 300 grams per decimeters cubed. So we have a concentration there of 300 grams per decimeters cubed. The student used 50 centimeters cubed of the copper chloride solution in the experiment. So the volume is 50 centimeters cubed. Now we need to change that centimeters cubed into decimeters cubed. So to do that, we would do 50 divided by 1000, and that would give us 0.05 decimeters cubed. And then to work out the mass, we are going to do the concentration times the volume. So we would have the concentration, which was 300, times the volume, which was 0.05, and that would give us a mass of 15 grams. Now, in this next question, we're being asked to compare sodium with chlorine. So we need to write some differences between the two. Now, if we look at sodium, sodium is in group 1, so it has 1 outer electron, and chlorine is in group 7, so it has 7 outer electrons. Now, in terms of similarities, what we can say, first of all, neither of them are in group 0, so neither of them have a full outer shell. So for the next part of the question, we have sodium atoms react with chlorine atoms to produce sodium chloride. Describe what happens when a sodium atom reacts with a chlorine atom. Write about electron transfers in your answer. And it's a 4-mark question. So we would say that the sodium atom transfers its 1, so we have to say how many, 1 outer electron to the chlorine atom. And this means that the chlorine atom gains one outer electron to have a full outer shell. So you get a mark for saying the sodium atom transfers its one outer electron to the chlorine atom, which gains one outer electron to have a full outer shell. For this question, it says the reaction between sodium and chlorine is an exothermic reaction. Complete the reaction profile for the reaction between sodium and chlorine. So first of all, because it's exothermic, the products would be below the reactants. So the product line must be lower. And then to show the reaction profile, we would do the activation energy and then the line would come down and meet where the product is at the bottom there. If it was endothermic, then we would draw this the other way around, so the products would be higher than the reactants, but because it's exothermic, the product is lower. In this next question, a student plans a method to prepare pure crystals of copper sulfate. So that's what we need to end up with. The student's method is we're adding 1 spatula of calcium carbonate to dilute hydrochloric acid in a beaker, and when the fizzing stops, we're heating the solution with a Bunsen burner until the liquid is gone. So we're told that the method contains several errors and does not produce copper sulfate crystals. And we've got to explain improvements that we could make to make sure that we are producing copper sulfate crystals at the end. So first of all, if we look at the initial stage, we're adding 1 spatula of calcium carbonate to our acid. Now, we need to start off with a carbonate that contains copper if we are to make copper sulfate. So what we could say is we would want to use copper carbonate instead of, we would want to use copper carbonate instead of calcium carbonate to start with. Also, if we're producing copper sulfate, the acid that we need to use to produce a sulfate needs to be sulfuric acid, not hydrochloric acid, because hydrochloric acid would produce a chloride, not a sulfate. So our second change should be that we need to use sulfuric acid, not hydrochloric acid. Now, when we're adding our copper carbonate to our sulfuric acid, we need to keep adding our solid until it's in excess, and we know it's in excess because no more would dissolve. Then to remove any of the solid that is remaining, we need to filter our solution that we have. And then finally, we need to heat our solution gently until the crystals start to form, and then we leave them and they will just cool and form in our evaporating dish slowly. And that would give us our 6 marks. In this next question, we are looking at the halogens. So the first question is, write the state symbol for chlorine at room temperature. Chlorine is a gas at room temperature, and the state symbol for a gas is G. For the next part of the question, we need to complete the dot and cross diagram for a fluorine molecule. And fluorine is in group 7, so each of our fluorine atoms would have 7 outer electrons, with one being used in our covalent bond. There we go. Now, for the next question, it says a fluorine atom can be represented like this. What is the total number of electrons in a fluorine molecule? So, if we know that one atom of fluorine has 9 protons, so it has 9 electrons, if we have 2 fluorine atoms in our molecule, that's going to be 9 times 2, so that would be 18. And then aluminium reacts with bromine to produce aluminium bromide. Complete the balanced chemical equation. So first of all, we need to write the symbol for aluminium bromide, which would be AlBr3. And then we need to balance up. So if we look, we have 2 times the aluminium bromide molecules on the right hand side, so that means we have 2 aluminium atoms which need to be balanced out on the left hand side, and because we've got 2 times the Br3, that gives us 6 altogether. So if we've got a Br2 molecule, 3 times 2 is 6, so that would balance that out. For this next question, it says when chlorine reacts with potassium bromide, chlorine displaces the bromine. Explain why chlorine is more reactive than bromine. And it's 3 marks for this question. So first of all, because chlorine is higher in the group compared to bromine, chlorine is a smaller atom with less energy levels. Now, because it's got less energy levels between the nucleus and the outer shell, that means there's less shielding. Because there's less shielding between the nucleus and the outer electron shell, the chlorine should therefore be able to gain an electron from another atom more easily. Now, quite often we get a question to do with structure and bonding. In this particular question, we have a diagram of diamond, and it's telling us that diamond has a high melting point, and we've got to explain why this is for 3 marks. So first of all, we would say that diamond has a giant covalent structure. And this means there are lots of strong covalent bonds. And if it has lots of strong covalent bonds, then lots of energy is needed to break them. And that's why it has such a high melting point. In this question, we have a diagram of sodium chloride, and we need to explain the conditions needed for the sodium chloride to conduct electricity. So first of all, we need to recognise that in the diagram, the sodium chloride are crystals, so they're solid, and the ions are not free to move. So we need to get these ions to be able to move for it to conduct electricity, and we would do that either by dissolving the sodium chloride in water or by heating the sodium chloride up so it melts and the ions are free to move. In this next question, we have the structure of sodium, which is a metal. So we have the positive ions, and they'll be surrounded by the outer electrons from the outer electron shells. And the question says, describe how sodium conducts thermal energy. So firstly, we have to recognise that the outer electrons from the outer electron shells which overlap are free to move. And because they're free to move, they're able to transfer energy throughout the structure. A group 2 metal carbonate thermally decomposes to produce a metal oxide and a gas. Give the formula of each product when calcium carbonate is heated. So if we have a metal oxide, that would be our calcium oxide, and the gas produced because we have carbonate would be carbon dioxide. The relative formula of a group 2 metal carbonate is 197. The relative atomic masses of carbon is 12 and oxygen is 16. Calculate the relative atomic mass of the group 2 metal. And then we've got to name what the group 2 metal would be. So you would need to make sure that you got your periodic table for this. So first of all, we've got to work out what the mass of the carbonate part would be. And the carbonate part of the metal carbonate is CO3. So that means we would have one carbon with a mass of 12 plus 3 times the mass of oxygen, and that gives us a total mass of 60. So then if we take the carbonate part away from the total mass of the metal carbonate, so that would be 197 subtracting the mass of the carbonate, and that leaves the mass of the metal to be 137. And then you look on your periodic table to find which element has a mass of 137, and that would therefore be barium. Now in this next question, figure 8 shows the volume of gas produced when a different group 2 carbonate W is heated. Calculate the gradient of the line in figure 8, and we need to give the units. So first of all, we've got to remember that the gradient of a graph is the change in y divided by the change in x. And if we use our graph here, I'm going to use it just to make it as easy as possible when we have our mass of group 2 carbonates in grams at 2, because that would just, for me, that I just think that's the easiest one to use. So I draw a line from there, and then obviously we have our line at the bottom there as well. Now, the change in y, if we look here, up to there we've got 300, and because we can see that every 5 small squares is 50, that means one small square has to be 10. So if we're going up from 0 to here, our change in y is 330 centimeters cubed. And because we've gone along to the 2 grams here, so our change in y is 2.0 grams. So if we put that into our calculation, change in y is 330 centimeters cubed divided by our change in x, which was 2.0 grams. The gradient works out at being 165, and if we're going to work out the units, we can see we've got centimeters divided by grams, so that's going to be centimeters cubed per, because it was divided by grams. Now for this next question, we're told that we've got 24 decimeters cubed of a gas, and when 1 mole of a group 2 carbonate is heated. we've got to determine the relative formula mass of the group 2 carbonate W, and we've got to use our graph to do this. Now, our graph does not go up to 24 decimeters cubed, but we could have a look at 240 centimeters cubed and work out what the mass would be for 240 centimeters cubed. And I've drawn that onto the graph, and we can see that 240 centimeters cubed of our gas produces 1.45 as a mass for our metal carbonate. Now, in terms of scaling up and ratios, we want to change 240 centimeters cubed into 24 decimeters cubed, which is 24,000 centimeters cubed. So to do that, we are scaling up by 100. So we have to times 240 by 100 to get 24,000 centimeters cubed. Now, if I have to do that to the volume, then that means I would need 100 times the mass to work out the relative formula mass if I had 24 decimeters cubed. So if I do 1.45 times 100, that gives me 145 as the relative formula mass. In this next question, a scientist did 2 tests on 4 white solids, A, B, C and D. So he adds the sample of the solid to distilled water and stirs, and then measures the pH of the solution after test 1. And we have our results of the pH here. Now, the 4 solids that we have are magnesium oxide, phosphorus oxide, silicon dioxide, and sodium oxide. We are also shown the solubility of each of these, and then we've got to try and work out which of these solids are which, and we have 6 marks to do this. So to try and figure out which one is which, we've got to use both sets of data from Table 2 and Table 3. Now, if we look at our results in Table 2, you can see that A, we are told that we have no solid left. B, we are told that there is no solid left. C, we are told that we have some solid that remains. So that means not all of the solid has dissolved in the water. And D, we are told that solid remains. But the pH of D is 7 and the pH of C is 9, the pH of B is 3 and the pH of A is 14. Now if we look at Table 3, we're told the solubility per 100 centimetres of water. So I'm just going to use the names of the metal because I've not got enough room to write the full names down. So magnesium has a solubility of 0.01, so it's not very soluble, but it is a little bit soluble. We have the phosphorus oxide, which has a solubility of 52, so that's quite soluble. We have the silicon dioxide, which has a solubility of 0, so that means it doesn't dissolve at all. And then we have the sodium oxide, which has a solubility of 109, so that's the most soluble. Now we can see that we have got 2 which are either completely insoluble or slightly insoluble. If I have silicon dioxide, which has zero solubility, then what that means is that the silicon dioxide has to be D. The reason being, if none of the solid has actually dissolved in the water because the solubility is zero, the liquid left in the beaker is distilled water, which would have the pH of 7. That therefore means that my substance C would have to be magnesium oxide because I've got solid remaining in my liquid, and because I've got solid remaining in my solution, and because I've got solid remaining in my solution, that's indicating that it's only slightly soluble. And table 3 indicates the only other one that's only slightly soluble would be magnesium. This now leaves our sodium oxide and our phosphorus oxide. So both of these are soluble, the sodium oxide being much more soluble than the phosphorus oxide. And we can see that our two remaining unknown substances are A and B. Now the key thing here is sodium oxide is a base, so that's going to be alkaline. And the pH for the alkaline substance is A, which means A must be sodium oxide, and therefore the phosphorus oxide would be our solid B, which also indicates that it's going to be phosphorus oxide because it is an alkali. In this next question, 10 centimetres cubed of solution B is added to a beaker. Distilled water is added to the beaker until the final volume is 1000 centimetres cubed. And we've got a results table here showing our volume and our pH. We've got to calculate the value of X. So the key thing to remember is if we're diluting from 10 centimetres cubed to 1000 centimetres cubed, that is we're diluting by a factor of 100. Now, when it comes to pH, factor of 10 causes a change of 1 pH on the pH scale. Now, because we've got a factor of 100, that is 10 times 10. So that means rather than having a change of 1 pH, we are going to have a pH change of 2. And because we're diluting, the acid is going to get weaker, and if the acid is going to get weaker, the pH is going to increase by 2, so our final pH would be pH 5. This question is about iron. So iron reacts with dilute hydrochloric acid to produce iron chloride solution and one other product. Name the other product. So when we have a metal reacting with an acid, we get a salt plus hydrogen gas. So our answer here would be hydrogen. Now suggest how any unreacted iron can be separated from the mixture. Because iron is a metal and the mixture is a solution, we can filter out the solid. So this would be filtration. Then we have a reaction of magnesium with iron chloride, and we have a balanced equation given to us. We're told that the mass of magnesium is 0.120 grams, and we have the relative atomic masses of magnesium and iron provided for us. We've got to calculate the mass of iron in milligrams, so we've got to be careful of that at the end. Now, first of all, it's always important to write out what we have. So for our magnesium, we know we've got 0.120 grams. We know that the relative atomic mass of magnesium is 24. So we can work out our number of moles of magnesium, because moles is mass divided by our atomic mass. So we would have 0.120 grams divided by 24, which gives us 0.005 moles. Now, when we look at the ratio of iron compared to magnesium, 3 moles of magnesium will produce 2 moles of iron. So, to work out how many moles of iron would be produced from 0.005 moles of magnesium, it would be 2/3 of the 0.005. And if we calculate that out, the number of moles of iron works out to be 0.00333 moles. Now, to convert moles back into a mass, we would then have to rearrange our equation so that we know what mass is, and we would have mass equals moles times the relative atomic mass of iron. So we would have 0.00333 times 56, and that gives us an answer of 0.1866 grams, and that's for our iron. However, we don't want our answer to be in grams, so to convert it into milligrams, we would have to times our answer by 1,000. So if we have 0.1866 grams times by 1,000, that gives us an answer of 187. So we'll just do it to 0 decimal places, 187 milligrams. So our answer here is 187. Now, sometimes in science, there's more than one way to work out calculations. And so I'm going to show you an alternative way to do this calculation. So first of all, we can see that we have our magnesium, and 3 moles of our magnesium react with 2 moles of our iron. So if we work out the masses, the mass of magnesium is 24, so 24 times 3 is 72. So 72 grams of magnesium would produce iron. The atomic mass is 56, so 56 times 2 is 112 grams of iron. So 72 grams of our magnesium would make 112 grams of our iron. And I can use that ratio to work out how much 0.120 grams of magnesium would produce. So if we write magnesium and iron, so initially we're saying 72 produces 112 grams. Now, to work out how much 1 gram would produce, we can divide both sides by 72. So it's a ratio, whatever you do to one side, you have to do the same to the other. And if we did that, I would have that 1 gram of magnesium would produce 1.56 grams of iron. Now, I don't want 1 gram, I want 0.120 grams. So I would multiply my 1 gram by 0.120, which means I would do the same to the other side. I have to multiply by 0.120, and that means that 0.120 grams of magnesium produces 0.1866 grams of my iron. But I don't want my answer to be in grams. I need it to be in milligrams. So therefore, to change my grams into milligrams, I would do 0.1866 times 1,000. And if I give my answer to whole numbers, I get an answer of 187. And for our last question, we're being asked to explain which species is being reduced in the reaction between magnesium and iron chloride. And our answer needs to include half equations. So if we're looking at our magnesium is going from just being magnesium metal to becoming Mg2 plus. So that's losing electrons. That's not reduction, that's oxidation. If I look at my iron here, my iron, in terms of an iron, is going to be an Fe3 plus iron, and it's going to form iron metal, so it's going to have to gain electrons, and gain of electrons is reduction. So in terms of my half equation, if I have my iron written as an iron, that's 3 plus, and my 3 plus iron is going to gain 3 electrons. So the electrons have to be added to the actual iron, and that produces my iron atom. And we can see that we've got gain of electrons. And when we have gain of electrons, that is reduction. So it's our Fe3 plus, which is reduced. And that brings us to the end of this paper. I really hope you found this useful. If you did, please hit that subscribe button. You'll have easy access to content being added weekly, but also other past papers that I will go through, including biology and physics. So good luck with your assessments, and let me know if there's anything in particular in the comment section that you would like support with.